Okay, and again, as I say, nice job with the intro. What I want to do now is I want to kind of look at the mathematical side of why the graph has these behaviors. But I hope that you kind of say, okay, it's the same thing. But of course, if we look at the mathematical side of rational functions, we'll be able to figure it out for the next problem. And there actually will be many next problems. We're going to be on this for several days. All right, now it's going to kind of feel a little more mathematical also the next several days. I hope that that doesn't sort of turn you off. I'm just being honest with you. It's a little more mathematical. It's kind of sometimes a little theoretical. Eventually, we'll put this all together and hopefully you guys will realize, okay, what we're trying to do is we're trying to graph rational functions. Now, I know it's kind of obvious, but a rational function is a fraction. But the reason it's a fraction is because it has a denominator. I'm serious about this. If you didn't have a denominator, just imagine for a moment with me, if you didn't have a denominator, you'd actually be back to a good old parabola. But my point is, as soon as you put a denominator into a function, you create all kinds of special behaviors. Okay, it's just that denominator that does that. And the reason the denominator does that is because denominators have a tendency to be bad. Okay, it's not really that funny, but I'll probably say it that way to try to get you guys to realize that it's the darn denominator that gives us all of these behaviors. Why the denominator? Because the denominator, remember, cannot equal 0. If a denominator does equal 0, then we're dividing by 0. And we know that that's a bad idea. So let's start with the denominator. And let's think about the denominator. And let's think about the denominator equaling 0. I know it's a bad thing to do, but if you think about the denominator equaling 0, you're going to be well on your way to analyzing this function. Now, look at that denominator with me. I know it's bad, but it can be factored. And usually the rule of thumb is in math, if you can factor something, you should, because you'll probably be able to see things a little differently. Okay, factoring is a skill that we want to have in this class. Multiply to be -8, add to be +2. It's a basic factoring. Multiply to be -8, add to be +2. And you should be arriving at x plus 4, x minus 2. Now, we all know that that's the same as this original denominator, but it's so much easier to see when it equals 0. And of course, we've done this kind of thing other times. But now, when I get -4 and +2, I actually get these bad numbers. And those bad numbers are going to show up on your graph in a special way. They're going to show up on your graph as asymptotes. Now remember, I am kind of assuming that because you did the intro, that some of what I'm showing you here, that you say, yeah, okay, yeah, I saw that last night. But what I'm doing with you now is I'm showing you how you're going to make these sketches without a table of values, without a fancy graph paper. And one of the first things you do is you're just going to sketch your vertical asymptotes. You're going to sketch them as dashed lines, and you're going to label them, of course, as -4 and +2. Okay. Desmos. I'm talking about the graphing side of Desmos. If you have not typed this kind of function in before, I want you to participate in this. It's something that you're going to want to be able to do. Couple thoughts. First of all, when you're typing a fraction in the Desmos, you got to go heavy on the parentheses, just like you did probably with your calculator. You have to put parentheses around the numerator and denominator. That way, Desmos knows what's what. So again, use parentheses around the numerator Use parentheses around the denominator, and just practice it, experience it a little bit. Of course, it's the same graph that we got over the weekend. What you're going to find is that we're going to use Desmos as a tool to help us to fit the graph into these behaviors. And basically what I'm getting at right now is that we have some vertical asymptotes that seem to be clearly shown on this graph. What I mean is that we have a graph, a branch that is getting closer to that asymptote, but remember, it's not touching it. That's good though. That behavior right there is good. We have the same thing that we can see here. We have the graph getting close to these asymptotes. And then of course over here on this side. All I'm saying is that so far, so good. I also want you to be careful that you don't say, hey, Mr. Naylor, I could just type this into Desmos and kind of get this done a little faster. Is that okay? Well, I'll say that it's really not okay because you're going to want to learn how to do this mathematically, because there will be a day where we take Desmos away. We will take Desmos away. So we're thinking about some of this mathematically. We're also thinking about how Desmos shows us the same answer. It's all part of the package right now. Hey, do you see another boundary line? Maybe you saw it over the weekend. Maybe I can help you see it right now. It's a boundary line that is horizontal. Now I'm going to type in y equals 2. If you would like to type it in, you can. Or if you just want to look up here. But I want you to see that green, or whatever color it's showing up for you, that green boundary line, how it also seems that that represents an asymptote. And in fact, it does. Now, it's called a horizontal asymptote. And it actually has a similar behavior, meaning that the graph is going to get closer and closer to that value. The graph is going to get closer and closer to y equals 2. Okay, now Desmos is actually showing this because, well, the graph keeps getting, as we go out here to the left, keeps getting closer. And now there's something a little special that happened here. The graph actually did cross the asymptote. We'll talk more about that, but that's actually okay. But now that it's down here at the bottom, it kind of sneaks back up, a little bit of a curve right there, and it keeps getting closer and closer to y equals 2. Why is this? Why the number 2? You know, where did that come from? Is it just kind of just because? Well, it has everything to do with the equation. And if I can go back to the equation here, let's talk about this horizontal asymptote. I'm going to get a little mathematical with you. Are you guys all right with that? If you think about the numerator and denominator, and if you think about infinity, now just stop right there. The reason we're thinking about infinity is because infinity is what happens as I go to the left and right. And that's exactly where we see this asymptote. We see it as we go far to the left and right. So if you think about x going to infinity, if you think about basically x getting really big, and you think about the numerator and denominator, you would be able to come to the conclusion that the largest part of the numerator is going to rule, and the largest part of the denominator is going to rule. That's because if I plug big numbers into this fraction, the biggest exponents are going to have the most power. This measly little -8 is not going to have a big effect if x gets really big. So what I'm getting at is that you can simplify this equation. Yes, you can simplify this equation to just be the big exponents. Now, I don't expect you to have known this, but I want you to listen because it's true that the biggest exponents, by the way, the biggest exponents are called a degree. That's a word that we've used before, but we're going to see that again. So I take the degree, which is the biggest exponents, and I come up with this kind of the simpler equation. Now, there's something cool that happens with this simpler equation, and that is that the x squareds cancel. Now, since the x squareds cancel, that leaves me with just the coefficients. And it turns out that the coefficients, 2 over 1, would represent my horizontal asymptote. Hey, there's going to be more to say about that. But I just want to say one more time that if I take the biggest parts of my fraction, they're going to rule when it comes to infinity. And infinity is a horizontal asymptote because that's what's happening at the ends of the graph. We've got a couple more behaviors, okay, and then we'll do a new graph. But how about the y-intercept? You guys are going to learn that the y-intercept is always part of a graph. And the reason it's part of a graph is because it's easy to find. Remember, all you have to do is plug in 0. Now, if you plug in 0 to a fraction, you do have to be careful because, well, the number 0 can be sometimes a bad number. But if you plug 0 into this fraction, we want you to conclude that it's okay. But are you thinking about that? Are you able to conclude that with me? If I plug in 0, that means I get 0 squared in, of course, the numerator. 0 squared is 0. And then if I do a little bit of math in the denominator, I get 0 minus 8. Okay, that's all right. 0 minus 8 is negative 8. And yeah, 0 divided by negative 8. I know it's a fraction. Sometimes we're not sure, but hey, you can have 0 divided by negative 8. It's just equal to 0. Basically, that means that if you plug x equals 0, you get y equals 0. Of course, that's the y-intercept. Y-intercepts are special because they're easy to find. And we can see that on the graph that 0, 0 matches. So that's good. But normally where we have a y-intercept, we also have a conversation about the x-intercept. Can you read that purple? I like that color, but sometimes it's hard to see. But the x-intercept, well, it also involves 0. This time it involves setting the equation equal to 0. Now, when you set the equation equal to 0, once again, you kind of have to be careful. You always have to be careful when you're using the number 0. I want you to think about something with me here. This is kind of like an equation that I'm solving. I know, I hate to sound like a broken record, but it's a fraction that I'm solving. But if I multiply the denominator, now it seems like kind of like a big thing to do, but if I take that entire denominator and I multiply it to the other side, I'm able to make the whole thing cancel out. And it basically just leaves me with 0 equaling the numerator. Well, if 0 equals 2x squared, of course, x equals 0. Now, you might be saying that we already figured that out, but I just want you to see that if you set the equation equal to 0, you can solve for x. Again, it turns out to be the same point, obviously, because the x and y-intercept are the same. Rational functions, behaviors. Okay, we're just scratching the surface, but let's do a new problem. Let's do a problem that you didn't do last night that you don't maybe know what the answer is, but I hope you start to see that we can use some of the same methods to come up with these features. And then what we'll do is we'll stop and we'll summarize this. Before we summarize, I want you to have another problem that you can kind of analyze. Now listen, it's just straight up easier because it's not quite as complicated of a numerator and denominator. Okay? The other thing is that we start to realize that we're actually making a list of answers. You'll realize that pretty soon. The homework helper, I already put the list there for you. But let's kind of generate the list. First of all, the vertical asymptote. It's really the first thing that you're going to do. Remember how we did it over here? It's all about the bad numbers. The bad numbers come from the denominator. Some of these problems, you're just going to be able to look at them and say, oh, okay, I guess x equals -2. I'll be honest, that's what I want you to do. I want you just to look at the denominator and come up with that conclusion. Now, soon, if not right now, that means that there's a graph that has an asymptote. Some people will wait to do what I'm doing here. That is, I'm starting to make the graph, but I just kind of want to make sure it's clear that that -2, that's going to be a vertical asymptote on your graph. Continue. Horizontal asymptote. Horizontal asymptote. If you don't mind a little abbreviating there. Okay, now I told you it's going to be a little mathematical. Maybe what I did over here was a little fancy, but I'm trying to help you guys understand why the horizontal asymptote always has to do with x going to infinity. Now, what that really means is x gets really big. And when x gets really big, all you have to really focus on are the big parts of the numerator. Now, kids, there's only one thing in the numerator, so by default, it's the biggest one. But I want to make sure you understand that that's because it has a degree. I shouldn't say it's because it has a degree, but I want you to know that the degree is 0. Now, it's really just the number 3, but it has a degree of 0. The denominator, however, has a degree of 1. I hope you notice that I'm looking at the x because that's the biggest part. Bottom line is I take the biggest part of the numerator and denominator and I make a simple fraction where I can think about x getting really big. Now, this is kind of like the chocolate problem from Friday. It's kind of like saying, what if I want to give the chocolate to an infinite amount of people? Well, we know that if we give the chocolate to an infinite amount of people, that it's going to approach a certain number because 3 divided by a big number is going to approach 0, but it's not going to equal 0. If I'm going to approach 0 but not equal 0, that's exactly what we're talking about. It's an asymptote. It's a boundary line. The horizontal asymptote always has to do with the numerator and denominator, and basically you compare them. Now, I will have kids ask, is it always going to be 0? Well, it's always going to be 0 if the bottom is bigger than the top. Listen, when I say the bottom's bigger than the top, that means x to the first is bigger than x to the 0. Now, we will make that conclusion in just a few moments. Let's find the y-intercept. Okay, the y-intercept. It's supposed to be an easier point to find. But again, anytime you're using the number 0, you got to be careful. So I'm going to show the work. Maybe you're just doing that mentally. Because if you do it mentally, you realize that you just end up with 3/2. Okay, yeah, 3/2, that's like 3 divided by 2. That's, if you prefer, that's 1.5. But hey, that's a y-intercept. In fact, it's 0, 1.5, if you want to write it as a point. And that means that it's on the graph. That means it's a point on the graph. X-intercept. X-intercept. Again, it involves 0. This time, it's the equation equaling 0. Look, anytime you have a fraction, anytime you have 0, you just got to be careful. And you really should be looking at this and saying, okay, how can this fraction equal 0? Well, I got news for you. Not if the denominator equals 0. Okay, we already figured out that the denominator is a bad place. So there's no way that the denominator can equal 0. That's why if I multiply it over here, it just kind of wipes out. It also kind of leaves me with a strange result, 0 equals 3. Okay, 0 equals 3 is a false statement. But what that really means is that there's no way that we can equal 0. Because, well, the numerator is already equal to 3. That means there's no x-intercept. Again, because there's no way to make it equal 0. Now, everything that we sketched over here is 100% right. But I want you to invoke Desmos. I want you to use Desmos to see how it all ties together. So, whoops. So, I encourage you to participate, and you can also watch. But basically, you type this thing in, and as you're going to get better at this, you say that we are right. You know, that these branches actually tie into what we already drew. So tie them in. You know, draw the branch, tie it in, draw the branch. Understand, please, that the point of this, of the next couple days, is to graph these. But maybe you caught me saying, I don't want you to kind of sneakily say, well, Mr. Naylor, I'll just graph it up here and I'll kind of make it look like that I did this. Trust me, you got to do this. Eventually, we're going to take Desmos away anyway. Okay, but it's kind of part of doing it a little bit mathematically and then a little bit with some technology. Okay, but it's all good. It's matching nicely. Let's summarize this a bit. Maybe you want to call it rational rules, but let's summarize how we find all this stuff, starting with the vertical asymptote. I'll tell you, it is the main idea. It will always be the main idea because you get a 0 in the denominator. If you like the way I worded it here, x equals a, x equals a, it's going to be a vertical asymptote if you get a 0 in the denominator. Remember the first problem we did. We actually factored the denominator to help. The second problem we did, honestly, we just looked at the denominator. But it's all about the denominator. Now, the horizontal asymptotes, sometimes initially they seem a little tricky to kids. It really boils down to 3 scenarios. I showed you 2 of them already. Let's try to summarize. It's all about the numerator and denominator. Now, make sure you realize I abbreviated some words up here, otherwise I couldn't fit it on the screen. But this is basically saying that the denominator is greater. I'm trying to help you get like the main idea. This says the denominator is greater. And if the denominator is greater, then it's always going to be y equals 0. Now listen, when I say the denominator is greater, I'm talking about the degree. Degree just means exponent. So we have x to the first in the denominator. We have x to the 0. We said that it's kind of weird, it's not written, but technically it's x to the 0. the denominator is greater. So if the denominator is greater, that means we're trying to give chocolate to an infinite amount of people. That's going to get closer and closer to 0. Okay, and again, it's always y equals 0. This is the one that people kind of like because it's easy to see. It's easy to see when they are equal. Again, when the numerator has a degree that's equal to the denominator. So when they're equal, then we get what I like to call A over B. A over B. Even if you feel like you know what I'm going to say, I still want to make sure you have the idea. The first problem we did, the one that you did as an intro over the weekend, the x squareds, the degree, were equal. When the degrees are equal, then you're able to, honestly, real simply, take the coefficients, 2 and 1. The coefficients, 2 over 1, create my horizontal asymptote. When the degrees are equal, it will work that way every time. There's one more scenario. It's the scenario where the degree of the numerator is actually bigger. In other words, it's kind of top heavy. Now, if the degree of the numerator is bigger, you didn't see this yet, but there will not be a horizontal asymptote. If you're wondering what that looks like, again, we can't do everything in one period, but you'll see. You'll see what it looks like if there's no horizontal. Again, the answer is always none. Now, the x and y intercept. You studied them back in Algebra 1, but they still apply today. Just remind yourself how you use 0 for the y-intercept. And then how do you use 0 for the x-intercept? Okay, most kids realize that you just got to be careful because when you're messing around with a fraction and you're messing around with the number 0, you got to make sure that you know what's allowed and what's not allowed. And that's why I want to do another problem, a problem that obviously looks a little different, hoping that we get even a little bit closer to starting to understand these rational rules. Okay, now this is a lot for one day, but it's nice to do this third problem. You start to have a little bit more to compare and build off of. This negative sign would be in front of the fraction. And we'll have to see what's what with that. All right, the opposite of 4x plus 16 all over 2x minus 4. Ready, set, here we go. Okay, now vertical asymptote. It's kind of really where all this has started. That's because it has to do with the denominator. The denominator equaling 0 is, of course, a bad idea, but that will give you a bad number. Now, maybe a problem like this, you feel like you have to kind of solve, like add 4 and divide by 2. Of course, you don't need to show that if you really don't need to show that solving. But x equals 2 is our bad number. I'm going to go ahead and wait to draw my sketch until the very end. Horizontal asymptote. Now, you should be concluding that the degrees are equal. Hopefully that kind of grabs your attention. But before we just very quickly grab 4 over 2. Now, that definitely is a big part of this answer. We should feel like that negative sign is being improperly ignored. In fact, that negative sign, as maybe we would remember, has to apply to one part of this fraction. Most kids will apply the negative sign to the numerator. Now, if you apply it to the numerator, what you're really doing is distributing it. So I'm going to say that it's going to be better for us to work with that version so that when we put a box around a over b, that we actually grab the negative sign with it. So we get negative 4 over 2 or negative 2. Now again, you see we just followed the rule. The reason that that's the rule is because x goes to infinity is going to be overpowered by just these two parts of the fraction. Okay, a over b. Y-intercept. When you plug a 0 into the equation, make sure that you take into account every part of the equation. Like, I'm talking about this negative sign once again that we distributed. I really need to take that into account. In other words, I need to use that version. So it looks like I get negative 16 over negative 4. Well, negative 16 over negative 4, trust your math, is going to come out to be positive 4. Okay, I got a y-intercept at 0, positive 4. And then the x-intercept. Now, the x-intercept is when the equation is equal to 0. Maybe you've noticed now that it's the third time that we've done this. The only way for an equation to equal 0 is if the numerator is equal to 0. The denominator is not allowed to be part of that. So could I just take negative 4x minus 16 and let that equal 0? Yeah. So this negative sign right here, this negative sign, I just said it verbally, but I'm glad you asked. It applies. And yeah, that's important because that's going to have a bearing on solving this, right? You're going to solve this, add 16, divide by negative 4. Now, I just said that verbally, but add 16, divide by negative 4 gives you negative 4. Just have a few moments to graph this. Now remember, no Desmos yet. You really should play along like that. No Desmos yet. Instead, I trust what I did. I graph x equals 2. I trust what I did. I graph y equals negative 2. Now be careful. It's just simple things like putting negative 2 down at negative 2. And then the x and y intercept. Be careful. Don't switch them. Like, on a good day, 0, 4 is on the y-axis. And on a good day, negative 4, 0 is on the x-axis. So, put them where they're supposed to be. Soon, you guys will look at that sketch, and you will already predict what Desmos is going to show. But right now, I want you to ask Desmos to show. I want you to ask Desmos to show you the graph. So if we ask nicely, Desmos will give us a good sketch. But what I hope is that you're looking at that and saying, that fits perfectly into these behaviors. I didn't really scale it as well as I should have, but that fits in nicely. It's approaching the asymptotes. And then I have this branch down here that's doing the same thing. Again, soon, if you guys keep coming back and you keep paying attention, you'll draw that graph without the help of Desmos. There's three homework problems, and there are some answers at the bottom. Okay, make sure though that you're not looking at the answers or not looking at Desmos too soon.